Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it. All right, I just read something that genuinely floored me. We talk all the time about the AI boom, about how fast it's growing, but this research out of Tufts University, they're claiming a 100-fold efficiency gain in AI training, 100 times less energy. That's not just a little better, that's a paradigm shift.
Yeah, and it's certainly a juicy headline, but let's be real, we've seen these kinds of claims before. This isn't about training the next ChatGPT. This is for robots stacking blocks in a highly controlled environment. It's a very specific application.
But even if it's for robotics, a 100x reduction in training energy and a 20x reduction in operational energy for an AI brain is absolutely wild. Imagine what that does to the economics of, say, an Optimus bot or an autonomous vehicle. That's not just marginal improvement, that's rewriting the rules of physics for hardware design.
It could be, yes, but we have to ask the bigger question. Does this block stacking breakthrough actually address the looming energy crisis that the AI industry is hurtling towards? Because right now, the entire sector is on a collision course with the global power grid, and it's not going to be pretty.
Okay, you're right. Let's start there, because the numbers are genuinely terrifying. We've talked about it in abstract terms, but the data from the International Energy Agency, the IEA, is just staggering. It's not just software anymore. It's an infrastructure and energy crisis.
Exactly. And people tend to think of data centers as these clean, ethereal cloud things, but they are absolutely physical, power-hungry behemoths. The IEA's special report, Energy and AI, showed that global electricity consumption by data centers hit around 415 terawatt hours in 2024. That's about 1.5% of total global electricity. Doesn't sound like much until you see the growth curve.
Which is where it really gets gnarly. They project that by 2030, in their base case scenario, that number more than doubles to 945 TWh. And this is the part that hit me. 945 TWh is equivalent to the entire current power consumption of Japan, the whole country.
And it gets worse. In the US, data centers are expected to consume more electricity by 2030 than all energy-intensive manufacturing sectors combined. That's aluminum, steel, cement, chemicals, everything. It's a truly massive footprint. As IEA Executive Director Fatih Birol said, AI is one of the biggest stories in the energy world today, and it's largely unspoken.
It's also not spread out evenly, which is what's going to physically break regional grids. I mean, nearly 80% of this growth is concentrated in the US and China. In places like Ireland, data centers already consume over 20% of the nation's electricity, and it could hit 32% by 2026. Virginia, the data center capital, is at 26%. They simply can't get the power.
It's the concentration that's the real issue. Imagine trying to power a new city's worth of computing infrastructure in a single county. That's what's happening. And the fundamental why behind all this energy consumption is the brute force nature of modern AI. These massive language models, their robotic cousins, the visual language action models, they're just glorified statistical probability engines.
Right. They don't think in the human sense. They're basically guessing the next word, the next pixel, the next robotic movement based on trillions of parameters. It's like using a supercomputer to figure out what 2 plus 2 is by analyzing every math textbook ever written instead of just using a calculator.
Exactly. They rely on these massive power-hungry GPU clusters. Matthias Schetz, one of the researchers from Tufts, pointed out that the energy expense of traditional AI is often disproportionate to the task. It's incredibly inefficient for logical tasks because it's just firing billions of neurons to statistically guess an answer. That's why you need server farms the size of small cities.
Which brings us back to Tufts. If we're staring down this energy cliff, how are these researchers proposing we swerve? What exactly is this neuro-symbolic AI that's getting these incredible efficiency numbers?
So the team, led by Professor Matthias Schutz, were specifically targeting visual language action models, VLAs. These are essentially LLMs given eyes and a body. They take visual data, text instructions, and translate that into real-world physical actions for robots. This isn't just about chatbots.
So it's about making robots smarter and more efficient in the physical world. And the key is this neuro-symbolic architecture. Help me unpack that, Because it sounds like a blend of old and new AI approaches.
It absolutely is. You have to think about the history of AI. Back in the 70s and 80s, we had symbolic AI, often called good old-fashioned AI, or GoFi. This was all about hand-coding explicit, rigid rules. If X happens, do Y. It was very logical, very energy efficient, but it was incredibly brittle. The real world is messy. You can't hand-code a rule for every shadow, every accent, every slightly different object. It failed because it couldn't handle the messiness.
And then came the neural era, which is where we are now with deep learning. That's the messy pattern recognition part, the system one thinking, right?
Precisely. Neural networks are phenomenal at pattern recognition, identifying a cat in a blurry photo, understanding nuances in speech. But their Achilles heel is strict logic. They often hallucinate or make statistical errors when strict rules are required. They're good at intuition, terrible at formal reasoning.
Okay, so neuro-symbolic AI is the synthesis. It's bringing those two together. So how does it work in practice?
Think of it like Daniel Kahneman's thinking fast and slow. The neural network part is system one, fast, intuitive, pattern matching. It handles the perception, like seeing a table and recognizing blocks, dealing with varying lighting, shadows, all that real-world messiness. But then the symbolic logic engine kicks in. That's system two, slow, deliberate, rule-based. It applies hard-coded rules of physics, sequential planning, and game logic.
So instead of the neural net trying to statistically guess if gravity still works, the symbolic layer just knows it does. It's not reinventing the wheel every time.
Exactly. As Schutz explained, a neuro-symbolic VLA can apply rules that limit the number of trial and error during learning and get to a solution much faster. It cuts out massive amounts of unnecessary computation. It doesn't have to learn from millions of examples that you can't put a bigger block on a smaller one. That rule is baked in.
That makes intuitive sense for efficiency. But how do you prove something like this isn't just theoretical? How did they benchmark it against traditional AI to show it actually works?
This is where it gets really compelling, because they chose a classic benchmark that specifically tests sequential, logical reasoning, the Tower of Hanoi puzzle.
Oh, the 3 pegs and the different sized disks? You have to move the whole stack, but you can only move one disk at a time, and you can't put a larger disk on a smaller one.
That's the one. And it's notoriously difficult for standard AI models because it requires strict, long-horizon sequential planning. If a traditional VLA model relies purely on statistics, it'll eventually make a statistical error, a hallucination, and try to place a large block on a smaller one, or misinterpret a shadow and knock the tower over. A single mistake invalidates the whole sequence.
So how did they fare? Did the neuro-symbolic model actually perform better?
Better is an understatement. It absolutely crushed it. Standard VLA models struggled significantly. They just repeatedly failed because of their statistical guessing and lack of rigid logical constraints. The neuro-symbolic VLA model, however, performed dramatically better. Because the symbolic layer explicitly understood the rules, it didn't waste time guessing invalid moves.
Wow, that's a huge difference in performance. But the real test for any AI is always how it handles something it's never seen before, right? The generalization aspect.
You got it. They then presented the robots with an unseen, highly complex variant of the puzzle that was not included in their training data. Standard VLA models, unsurprisingly, failed every single attempt.
Okay, but the neuro-symbolic model, please tell me it did better.
It still performed remarkably well. Think about that. A novel, complex problem it hadn't specifically trained on, and it still got it right most of the time. This shows it's not just regurgitating memorized training data. It's actually applying logical rules to solve a novel problem by breaking abstract tasks into fundamental categories, like block shape and centers of mass. That's genuine problem solving.
That's where the smarter, not harder really comes into play. It's not just about brute forcing an answer, it's about understanding the underlying rules. And this is where we get to the headline-grabbing numbers, the 100x claim. How does this translate to actual energy and time savings?
This is where the efficiency miracle truly shines. Training an AI model is usually the most energy-intensive part of its life cycle. We're talking massive data centers running for weeks or months. For the standard VLA model, training took a significant amount of time. The Neuro-Symbolic system, it was fully trained in a fraction of that time.
A fraction of the time? That's not a small improvement. That's a different universe.
It absolutely is. And because the training time was so dramatically slashed, and the model didn't have to blindly compute millions of trial and error permutations, training the neurosymbolic model required only 1% of the energy used by the standard VLA system. That is the literal 100x energy reduction they're claiming.
So 100x for training. What about when the AI is actually doing something? The operational phase, or inference as they call it.
The savings continue. When the neurosymbolic model was actively executing tasks, they found it used just 5% of the energy required by conventional approaches. That's a 20x reduction in operational power.
Okay, so 100x for training, 20x for operating. This changes everything for physical robotics. If a robot needs 20 times less power to think and process its environment, it means smaller batteries, lighter robots, much longer deployment times, vastly cheaper hardware. You're moving the heavy lifting from brute force hardware to elegant software architecture. This is huge for edge computing, for anything that runs on a battery.
It's the fundamental shift. Think about autonomous vehicles. Right now, self-driving cars need massive, power-hungry compute trucks to process all that visual data. Imagine slashing that power draw by 95%. That's more range for EVs, less heat generated, more reliability. For industrial robots like those Amazon uses or Tesla's Optimus, a 20x reduction in operational energy changes the unit economics completely. It moves them from science projects to commercially viable workforces.
I'm seeing this as a massive win for battery-powered devices. But let's bring it back to your earlier skepticism. This was a block stacking robot. Can this 100x miracle scale to the massive enterprise large language models that are currently draining the grid? Can this save us from the ChatGPT energy crisis?
And this is the crucial question, the big if. The Tufts team achieved this incredible efficiency in a highly structured physical environment using VLAs. The open question in the tech press is whether you can apply this neurosymbolic architecture to massive LLMs like GPT-4 or Gemini.
So what's the catch? Why can't we just plug symbolic logic into an LLM and make it 100 times more efficient?
The challenge is known as the knowledge acquisition bottleneck. Symbolic logic requires humans to explicitly define the rules. It's relatively easy to define the rules of physics for wooden blocks, solid objects cannot pass through each other, larger blocks cannot go on smaller blocks. But how do you write explicit mathematical rules for writing a Shakespearean sonnet, or drafting a legal brief, or generating a video of a dog riding a skateboard?
Because human language and creativity are inherently messy and often rule-breaking. Pure neural networks dominate text and image generation precisely because they don't rely on rigid rules. They capture the messy, statistical nuances of human data.
Exactly. Trying to force symbolic rules onto that kind of open-ended creative output seems incredibly difficult, if not impossible, with current approaches. So, scaling neurosymbolic AI to replace enterprise LLMs in massive data centers remains incredibly difficult and unproven. I don't see Sam Altman knocking on Professor Schutz's door tomorrow to re-architect GPT-5.
Okay, fair point. But even if neurosymbolic AI never replaces ChatGPT, does it matter? The robotics and edge computing market is massive enough on its own to be a multi-trillion-dollar disruption. I mean, autonomous vehicles, industrial robotics, smart grid management, these are all critical rule-bound applications.
You're right. Even if it stays in its lane, that lane is huge. For smart grid management, for example, where you want strict adherence to safety rules and not statistical hallucinations, this kind of logical, rule-bound AI is perfectly suited. It's ironic. AI is needed to manage the complex renewable energy grids of the future, and this more efficient AI could be the key. Neurosymbolic AI offers a sustainable off-ramp from that brute force highway.
So let's recap some of the big takeaways here. First, we're facing a massive AI energy crisis, with data center demand projected to double to 945 terawatt-hours by 2030, which is more power than entire industrialized nations like Japan. It's a genuine threat to our energy infrastructure.
And the breakthrough from Tufts University is a neuro-symbolic AI that merges neural networks for perception with symbolic logic for rules. This isn't just a tweak, it's a fundamentally different way of building intelligent systems.
And the numbers are the miracle. On complex puzzles like the Tower of Hanoi, this hybrid model performed dramatically better than standard AI. And the efficiency metrics are just mind-blowing. 100 times less energy to train and 20 times less energy to operate.
But the critical reality check is that while it's revolutionary for physical robotics and edge computing, applying that rigid symbolic logic to the open-ended, creative world of large language models still presents a massive technical hurdle. The knowledge acquisition bottleneck is real.
So it begs the question, are we building the wrong kind of AI right now? Are we throwing gigawatts of power at statistical guessing engines when we could just be teaching them the rules of the game?
It certainly makes you wonder about the long-term sustainability of the current path. If I'm building humanoid robots or managing autonomous fleets, a 95% drop in the AI brain's battery drain is the difference between a toy and a viable product. It completely changes the economics.
And let's be blunt, Sam Altman isn't going to stop building massive data centers because of a block-stacking robot in Massachusetts. But if the grid literally cannot provide the power by 2030, then the industry will be forced to adopt these kinds of neurosymbolic efficiencies, whether they want to or not. It might not be a choice anymore.
It might become a regulatory or even a physical constraint that drives the innovation in this space, rather than just market preference. It makes you think about how much raw compute power we are literally burning through versus how much more elegantly we could be solving some of these problems. What happens when the efficiency imperative becomes the dominant force in AI development?
And what implications does this have for the fundamental architectural choices that are being made today for the next generation of AI? Are we setting ourselves up for an even bigger energy problem down the line if we don't start incorporating these kinds of lessons now? That's a heavy thought.
That's all for this episode of Tech Disruptions. Join us next time as we keep exploring the technologies reshaping our world. Thanks for listening. We'll see you next time.
Stay curious out there.